Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to this course on gas turbines and jet engines. So, today is lecture 20 of this course and this is the final lecture of week 4. Okay. So, we will continue our discussion on real gas turbines. Okay. We had discussed previously how the irreversibilities needs to be accounted for in the gas turbine and also the changes in kinetic energy. Today, we will discuss 3 more differences with ideal cycles. One is the pressure loss. So, pressure losses occur at many different locations. So, we will consider that. Then regenerator loss and then variation of properties, specifically Cp and gamma of the combustion products and air. So, concepts which will be covered as I have briefly explained. We have already covered the deviations of due to effect of kinetic energy and effect of irreversibility. Today, we will cover effect of pressure losses, effect of regenerator losses and we will discuss variation of Cp and gamma. So, effect of variation of Cp and gamma. Okay. So, let us start with effect of pressure losses. So, what happens is that till now we had considered that there are no pressure losses in any of the devices, like the constant pressure processes remain as constant pressure processes. But in reality what happens is that there are always minor pressure losses, particularly when we consider combustion chamber there can be quite significant pressure losses and also when a regenerator is present it is a heat exchanger. So, although it is modeled as a constant pressure process, but there are pressure losses in both sides of the regenerator. Okay. So, we will take up one schematic diagram to see how these effects. So, for example, let us say that these are 2 constant pressure lines, okay. And then this is another constant pressure line which is at a slightly lower pressure, and let us say another constant pressure line like this. And we will draw some more constant pressure lines and I will explain what we are doing. So, now for the compression process we are going from 1 to 2, right. So, we are going from, so this is 1, this is 2s. So, instead of 2s we will go to slightly higher entropy which is let us say 2. Now, if we have a regenerator, so this is with a regenerator. So, regeneration or regeneration okay, is present. So, due to the pressure loss in the regenerator there is a slight decrease of pressure in the air which is passing through the air side. So, after regeneration it will be somewhere around say this location. So, this will be our state 5. So, there is a slight drop, it is difficult to show here on at this scale, but it can be of the order of 2 to 3% of the compressor delivery pressure which is the pressure at state 2. Then from 5 we have inlet at the combustion chamber and again there is some pressure loss in the combustion chamber which cannot be avoided and ultimately we will reach a pressure which is slightly lower as compared to the other blue line. So, if I draw the pressures, this is one pressure drop and this is the second pressure drop that occurs in the combustion chamber. Let us call this as delta P Cc and this as delta P regenerator on the air side, okay, delta P regen A. So, 2 to 5 is the regeneration process, 5 to 3 is the combustion process. So, why is there a pressure loss in the combustion process? So, in combustion we need to sustain the flame, which means that if the flow is very fast through the combustion chamber and it is very streamlined, there will not be any locations where the flame can be sustained. Okay, the flame will blow out of the combustion chamber. So, there are devices which blocks the flow within the combustion chamber, as we will discuss later, and these are used for creating local pockets. These are known as flame holders. So, this creates local pockets where the airflow velocity is quite less and the flame can be sustained, and then the combustion can proceed. So, as a result, these are necessary, but create some pressure loss due to drag. Okay. Then on the gas side, we have the expansion in the turbine. So, the expansion in the turbine, what will happen now is that the pressure ratio is decreased as compared to the compressor pressure ratio. If the compressor pressure ratio is, let us say it is 10. Okay. So, for the turbine, because the pressure at the regeneration process itself is slightly lower, maybe 2 to 3% lower, and then in the combustion chamber again 3 to 4% lower, the overall pressure ratio will be slightly lower than 10. So, we get less work output from the turbine, although the compressor work remains same. So, we get so that is how the pressure losses affect the overall say performance parameters. The efficiency will get decreased, the work output will get decreased. Now, if there is regenerator present, even at the gas side also there will be pressure losses. So, the process will go something like this. So, this will be somewhere around 6. My diagram is not accurate. So, 6 has to be equal to or higher than the 0.2 and 5 has to be lower than the 0.4. So, 4 to 6 is the process in the gas side, at the gas side of regeneration, and this change, okay, this change here, this is the delta P or pressure loss in the regenerator at the gas side. Okay. So, what is this role? Then it also decreases the, it increases the exit pressure of the turbine. Okay. It increases the exit pressure of the turbine. As a result, the pressure ratio is further decreased. So, similarly, if there is a second combustion chamber, then in that case also there will be pressure losses. If there is an intercooler, then also there will be pressure losses. Okay. So, we need to account for that. So, how these are incorporated in calculations? We calculate the pressure, let us say we calculate the pressure P3 in terms of P1, or no, in this case this is P2 minus delta P regen A minus delta P Cc. So, this is the pressure. Instead of equal to P2, this is slightly lower than P2, and if we know what values do these parameters have, then we can find out what should be the pressure P3. Temperature of course is fixed. So, temperature will remain fixed equal to the turbine inlet temperature. So, which specifies the state, and we can proceed with the calculations. Okay. So, typically for regenerators or for combustion, typically for combustion, so regenerators may have 2 to 3% pressure loss. Combustion chamber for industrial gas turbines may have 2 to 3% pressure loss. 2 to 3% of what? 2 to 3% of compressor exit pressure. Okay. This is known as compressor delivery pressure. So, 2 to 3% of compressor delivery pressure. Okay. This is for industrial gas turbines, whereas for jet engines the pressure losses are higher. So, jet engines can be significantly high, it can go up to 6 to 8%, of the compressor delivery pressure. Why? Because in jet engines the air intake occurs at a high velocity. So, we do not reduce the velocity as much, and as a result holding the flame is more difficult. Industrial gas turbines are stationary objects, jet engines are moving with high velocity. So, in those cases holding the flame is more difficult. So, you need more cleverly designed flame holders, which results in more drag and more pressure drop, okay, but is necessary. And as I have already explained, the pressure losses reduce the net work output and consequently the efficiency. Okay. Calculation of pressure losses are not very difficult. So, next is effect of regenerator loss. Of course, this is only valid or only present when there is a regenerator. You will see that in most cases for jet engines there are no regenerators, but only for industrial gas turbines, large industrial gas turbines, regenerators are used. So, regenerator losses means that we are unable to use the entire energy which could have been theoretically taken from the exhaust gases. We are unable to use that entire energy for heating the air coming from the compressor. So, we have already defined a parameter called effectiveness. Okay. We have already defined a parameter effectiveness, which has a value between 0 and 1, and we had stated that. So, this effectiveness was defined in terms of the actual temperature rise by the theoretically maximum temperature rise possible. So, we will draw that and we will again confirm that. So, I will ignore the pressure losses now to keep the diagram simple. So, in these cases one to 2 is the actual compressor process, then 2 to 5 and 5 to 3 total will be the regenerator air side plus the expansion combustion process. This is 4. Okay. So, maximum theoretically possible temperature is, let us say it is 5 dash, okay, which is equal to 4, T5 dash equal to 4, T4. If that is the maximum theoretically means possible temperature, so that of course is dictated by what is the temperature at the turbine exit, because that is the maximum temperature of the exhaust gases. We cannot heat the air beyond the temperature of the exhaust gases, because exhaust gases are the source of heat. So, in that case, if we assume equal Cp, the temperature decrease at the gas side will be from 4 to 6 dash, but in reality what happens, we know that there is slightly less increase in the temperature. So, let us say that we go up to 5, okay, which is lower than T5 dash, and as a result on this side we go up to 6. Okay. So, we had defined this effectiveness as T5 minus T2. Okay. So, we have defined this effectiveness as T5 minus T2 by T5 dash minus T2, which is equal to T4 minus T2, and we had discussed previously that this has a value of somewhere, for typical cases this may be around 0.9, okay, around 90% effectiveness. We can of course by design increase this effectiveness if we have a larger surface area and we allow more time for heat transfer, but that will come at the cost of means much more pressure losses, higher cost, capital cost of developing or means manufacturing the regenerator, and also we cannot have more time because the time is dictated by how fast the entire process needs to be, okay, or entire cycle needs to be. So, we cannot allow for very long time for heat transfer. So, by using this effectiveness of the regenerator, we can incorporate the losses in the regenerator. Okay. More accurately, if we have variable Cp and variable Cp values, as we will see in the next slide, then accordingly we have to do the energy balance. If the Cp of air and Cp of gas is considered different, which we will do from next slide onward. So, in that case, and if the mass flow rates are different, which also will be the case later on, because the mass flow rate at the air side is equal to the inlet mass flow rate m dot A, at the gas side the mass flow rate is higher, which can be called as m dot G, which is equal to m dot A plus m dot F. So, mass flow rate of fuel is also added in the combustion chamber. So, if we consider these to have the equations more accurate, we will have m dot A Cp of air, because that is in the air side, T5 minus T2 equal to m dot G, Cp of gas, which will be different, and we will analyze this later, T4 minus T6. So, along with 1 we will use 2 for energy balance, and we can specify all the states from here. Okay. So, now we proceed to the next deviation from the ideal cycle, which is due to variation of the properties of the gases. What properties of the gases? To be more specific, the thermal properties which are important in this case is the Cp value. So, the specific heat and the gamma, which is the ratio of the specific heats. So, Cp and gamma are needed for calculating all the, or it is necessary, or it relates the enthalpy change with the temperature change and the temperature change with the pressure changes. So, any change in Cp and gamma also affects these relations. Okay. So, this Cp is dependent on both temperature and as well as the composition of the gas. Okay. We will see that. So, the temperature in the cycle we know varies a lot, it can go from 300 to 1500, 1600 Kelvin. So, although till now we have taken constant Cp, in reality it is much more accurate to take the variation of Cp as a function of temperature. Cp also is a weak function of pressure, but that can be ignored, and we can take Cp to be a function of temperature. Okay. So, already it is mentioned here that Cp can be taken as a function of temperature. Now, gamma, which is the ratio of specific heat, Cp by Cv. Okay. So, this is also dependent on the composition, okay. And Cp itself is dependent on composition, but gamma also. So, Cp depends on composition, gamma also depends on composition. We know that gamma depends on the nature of the gas, whether it is a monoatomic gas, diatomic gas, also depends on that. So, for combustion products we have carbon dioxide plus water vapor, which have more number of atoms per molecule as compared to say O2 and N2. So, as a result this is going to change, and also Cp variation will itself affect the gamma value. So, gamma is equal to Cp minus Cv, and we also know that R equal to, R is the gas constant, R is equal to Cp minus Cv, gamma is Cp by Cv, R is the gas constant, which is Cp minus Cv. Okay. So, we can write from here that so what we can do is we can write this as gamma equal to gamma or gamma minus 1, let us write this way. Okay. Gamma minus 1 equal to Cp minus Cv by Cv, okay. Or we can write this as gamma minus 1 by gamma. Okay. Dividing both sides by gamma, we have Cp minus Cv by gamma Cv, which is equal to Cp. Okay. We are writing it in forms of Cp and R, because those are the parameters which we generally use. So, this is equal to R by Cp. Okay. So, which means that gamma minus 1 by gamma. So, remember that R is the gas constant. So, we can write it in terms of the universal gas constant R bar divided by the average molecular weight, okay, multiplied by Cp in this case. So, R is equal to universal gas constant R bar divided by average molecular weight of the gases. So, we see that how gamma is a function of the average molecular weight as well as Cp, and Cp itself is a function of temperature. Okay. So, we need to account for different values of gamma and Cp as a result. So, ideally what needs to be done if we want very accurate calculation, we want to use a function for Cp and similarly we want to find the variation of gamma, and based on that, because our temperature rise itself will depend on these parameters. So, the temperature rise is unknown. So, assuming some value of Cp and gamma, we need to calculate the temperature rise, and based on that we need to calculate again the new values of Cp and gamma, and then we have to have a iterative process until we get a converse solution. Other way is to take these as functions and do direct integration based on functions, or use numerical integrations or numerical calculations. Okay. But in this course we will take a simpler approach. Okay. In this course we will take a simpler approach. So, we will divide the entire cycle into two different regions. One is the air side, which is the compressor, regenerator, air side, and the other is gas side, which is the turbine gas side regenerator, and for the combustion it is going from air to gas. So, accordingly we will take Cp values for quick calculation. So, this is what we will follow in this course. For quick calculations, we will take Cp to be equal to 1.005. For air, this is the standard value and this is what we have already considered, kilojoule per kg Kelvin, and gamma also we know is 1.4. This is for air. Okay. So, for the compressor. For combustion products, we will take a different average value. So, it is seen that this is a good approximation. Cp is equal to 1.148 kilojoule per kg Kelvin. So, higher value of Cp, and gamma also can be obtained from this, and that comes out to be 1.333. Okay. I was wrong in the beginning, actually I misspoke that gamma will depend on the number of atoms, but it is the other way around. So, monoatomic gases will have higher value of gamma and diatomic gases will have lower value. In this case it is even lower because we have CO2 and H2O. So, this is valid for turbine, this 1.33. So, for turbine or the expansion process where we have combustion products, we will take this value of Cp and gamma 1.148 and 1.333, whereas for the compressor and air side calculation we will take 1.005 and 1.4 as gamma. Okay. So, we have to be careful. If we need more accurate calculation, we need to consider the variation with composition and temperature, and for that to get very accurate variation with composition, we need to solve for the change in composition, which means that we need to find the concentration of various reactants and products, which itself will be a very involved task. So, now we will finish this class with a simple numerical example to illustrate how these calculations are done. We could do similar calculations for the pressure losses also, but to save time I am just taking one of the deviations, which is the variation of Cp and gamma, and we will solve a problem for that case. Okay. we will solve a problem where there is difference in the Cp and gamma, and this we are doing so that we know how to solve similar problems in future. Okay, what values to take and how to do the calculations, very simple, just for illustration. So, we have a gas turbine with a compressor pressure ratio of 10 without any losses. However, and also the temperatures are given. Okay, now, let us use stagnation values to make it more accurate. T01 is 300 Kelvin, T03 which is the Tmax value is 1500 Kelvin, means the turbine inlet temperature. Cp and Cv are not constant, means they are different for the air and for the combustion products. For air and combustion products. Okay. So, the efficiencies of the turbine and compressor, both cases isentropic efficiency is given as 0.9 and there are no pressure losses, and we need to find out the states, the temperature, find the temperature after each process, okay, at the end of each process, or the states at the end of each process, pressures will be known. So, mainly finding the temperature. Okay. So, this is the problem. So, what we will do is we will just do this calculation, simple calculation, but we will take these accurate values of, means this new values of Cp and gamma. So, let us draw the cycle first for reference. TS diagram. So, going from 01 to 02, compression process, isentropic efficiency is 0.9. So, let us say that this is 02S. Now, isentropic efficiency is defined in terms of the stagnation or total temperatures and total enthalpy. Then 2 to 3 without pressure loss, 2 to 3 is the combustion process and 3 to 4 is the expansion in the turbine. Okay. Ideal state after expansion would have been 04S. So, cycle is exactly similar, only the values will change in this problem, similar to the first cases that we have studied. So, from 4 to 01 we close the process by a constant pressure heat rejection. Do not forget the arrows and the numbers of each of the state. Okay. So, in this case how do we proceed? Compressor calculation is exactly same as before. So, T02 by T01, only thing is that now we are considering stagnation states. So, first we need to find out T02S, T02S by T01 is R to the power gamma minus 1 by gamma, which can be used, okay, to get the value of T02S. Okay. So, this comes out to be equal to 579.2 Kelvin. By the way, we need to find the temperature at each state. So, 01 is already known, it is 300 Kelvin. 03 is already known, it is 1500 Kelvin. So, we have to find T02 and T04. Okay, we have to find T02 and T04. What are the pressures to specify this test? P01 and P04 are equal to the atmospheric or ambient pressure, and P02 and P03 is 10 times of that, because the pressure ratio is given. Okay. So, now using the isentropic efficiency relation, isentropic efficiency for this case is T02S minus T01 by T02 minus T01. Ideal temperature rise by the actual temperature rise, or ideal work input by the actual work input. So, this is given as 0.9. So, from here we get the value of T02, this comes out to be 610.123 Kelvin. This we have previously also calculated, you can match, it will be the same value. So, this is for the compressor. Now, for the turbine, we will follow same procedure, but take different values of Cp and gamma. So, for the turbine, T03 by T04S, this is equal to, so this is equal to R to the power gamma of gas. So, gamma G is gamma of gas, which is 1.333 minus 1 by gamma G. Okay. So, till now we have used only gamma, now we will use subscripts gamma A for gamma of air and gamma is G for gamma of gas. So, similarly here this will be gamma A and this will be gamma G, this will be Cpa and this will be Cpg. Okay. So, this is 10 to the power 0.333 by 1.333. Okay. So, this will give us the value of T4S, T04S, which comes out equal to 843.88 Kelvin. Again, I have done the calculations already, so I am directly writing the values. In your case, you should pause and you should try to do the calculations and match the values, verify the values. It can happen that my values may not be correct, your values can be correct, but the procedure is going to be correct. So, now using the definition of isentropic efficiency, which for turbine remember is T03 minus T04, actual temperature drop by ideal temperature drop, opposite of compressor, T04S. This gives us a value of T04 equal to 909.49 Kelvin. Now, if we had further proceeded with this problem, we have found the temperature, so this problem is solved, but if we wanted to find the work output from the turbine, in that case we will need to use the Cp of gas for calculating. So, the work output from the turbine Wt will be Cp of gas, which is 1.148 into mass flow rate. So, if we are doing the problem in terms of mass flow rate of per unit mass flow rate of air, this will be m dot G by m dot A, because that is the ratio of the mass flow rate. So, per unit mass flow rate of air in the turbine we have larger mass flow rate multiplied by T03 minus T04. This may be confusing now, but in the next class this will be clear. Okay. So, this is how you need to incorporate these effects. Similarly, for pressure losses also you can easily do the calculations, these are not difficult. So, in this class we have analyzed the effects of pressure loss, regenerator loss and the effect of variation of Cp and gamma due to temperature and composition. So, with this we stop today. These are the references, again the important books that we are following, and with this I thank you, and we will meet in the next class. Thank you.